so that kind of sums it up for the work on GANs. But again, some very interesting work that can be done with GANs, and a lot of CNNs that are used under the hood. So now I want to talk a bit about CNN datasets. So what are the typical datasets that we use for convolutional neural networks? So the one that we've seen over and over, of course, MNIST. So in the case of MNIST, we have 60,000 handwritten digits. They're all grayscale images. They're 28 by 28 resolution, so relatively small images. And this is a very easy to train network. And what I mean by easy is that most architectures that you will throw at it these days, you'll be able to find you'll be able to get some decent accuracy with it. And Gaetan also mentioned that it's been used so much and the test set has been evaluated so much. At this point, it might be that we're also overfitting in some sense on the test set as a community as a whole. So it's interesting to go past MNIST now and train on some other data sets. So for example, we have fashion MNIST. So I like to think of this as MNIST, but more fashionable. It's also a little harder, so we have a bit more than just edges in these images. It's still 10 categories, and it's still grayscale images. The categories range from sneaker to shirt to boot. And I like this quote from the creators: if it doesn't work on MNIST, it won't work at all. But if it does work on MNIST, it may still fill on other harder data sets. So this is more of a toy data set that's just slightly harder than MNIST to test your ideas on. So CFAR10, this is also a pretty widely used data set. It's relatively small in size, so 60,000 RGB images, and it's very low resolution. It can sometimes be very difficult to make out what's in these images. We have 10 classes with 6,000 images per class, and so you can see the different classes: airplane, automobile, bird, etc. So this is typically used for CNNs when we're dealing with RGB images to try out different toy models or toy experiments. And again, this is kind of in the same wave of MNIST. If it doesn't work on CFAR, it probably won't scale on larger data sets. That is, of course, until you start building much, much larger models that require in the order of millions of images. So after CFAR 100, there's CFAR 10, there's CFAR 100. It's the same size. It's also 60,000 RGB images. However, now there are 100 classes with 600 images per classes, and we have a different list of these classes here. So SVHN, this is also an interesting one, and again can kind of remind you of MNIST, but definitely harder. So in this case, we have multiple digits per image, and for each digit, we have the coordinates of the bounding box that surround the digit. And this was taken from Google Street View. So this data set was released a few years ago. And we have approximately here 600,000 labeled digits. So a lot more digits to train on. Color images. The images are not all of the same scale. So there's that scale that might be a little bit trickier to deal with when we're training. However, it's not always the highest of resolution images, and still, on most of the images, the digits are kind of the centerpiece of the image, so it could still be considered quote-unquote easier if you're trying to find numbers in the wild to do optical character recognition. All right, let's move on to ImageNet. And in my opinion, this is one of the most important data sets out there. It's one of the most widely used for image classification, and it's responsible for many, many important discoveries in CNNs. In fact, I would probably argue that if it wasn't for the ImageNet dataset, we probably wouldn't be in this room today, because a lot of important discoveries were made that have really made the community understand the power of convolutional neural networks. So ImageNet has thousands of categories and millions of images. So here we see just some different examples of categories, and they're very wide-ranging. So obviously we have the classic cat and dog, which we always talk about, but you even have like tandem bicycles and African chameleon. So all in the same data set, and your network has to figure out how to distinguish between a chameleon and a tandem bicycle. So you can imagine that your network has to have a certain capacity to be able to differentiate between these classes. So ImageNet is RGB images, but this time it's 256 by 256 resolution. So there's 3.2 million images that are manually labeled, and there are thousands of categories. And so ImageNet has a very interesting history. So this is Feifei Li. She's responsible for ImageNet. So there's a link here to the entire history of ImageNet, and I want to take some time to talk about it because, again, ImageNet is one of the bigger contributions that have happened so that deep learning can get to where it is. But no one took ImageNet seriously at first. When Fei-Fei Li first proposed the idea of gathering data for ImageNet, people sort of scoffed at her. They said, no way, this isn't going to work. In fact, according to this story, when she applied for grants, she was at Princeton, and she was told that she was an embarrassment to Princeton, and that the only reason that her grant proposal got as far as it got was that because she was a woman. So this is how it's really crazy. At the time, people were like, "Oh, we already have these data sets. We don't need larger data sets." But her intuition was great. Is that we have these really small data sets on small amounts of categories, but we need much larger data sets to be able to prove that deep learning works. And the first time that they collected ImageNet, she was only given a poster session. And today, again, ImageNet is just used almost everywhere. Almost every network is first tested on ImageNet. So we're going to talk more about ImageNet later today, and we're also going to look at all the different architectures that came out from ImageNet. So again, the take-home message is ImageNet is a really important data set, and it really just changed the game. We went from 32 by 32 images to really millions and millions of images on thousands and thousands of categories. So now we really had data sets that we could train really deep networks on. So another interesting data set is the Common Objects in Context data set. So it's the COCO data set. It was released by Microsoft. And this one has a lot less categories. So ImageNet has in the thousands of categories. This one has only 91 categories and 328,000 images. But what's really interesting about this data set is that the instances are all labeled independently. So prior to COCO data sets, if you wanted to do semantic segmentation, which we're going to look at later today, what that means in detail, if you had multiple objects of the same class in an image, you couldn't distinguish between them. So in this case here, we have many sheep, and your network learns that there are many sheep, and like your labels would say there are many sheep in this image, but it wasn't possible to distinguish the different sheep in the image. You just said, this pixel is sheep, this pixel is not sheep, this pixel is human. COCO data set, what they allowed you to do is to say, we are actually identifying every single instance in this image at a per pixel level resolution. So they give bounding boxes, but they also give per pixel resolution. And you have here a list of all these different categories here. So for example, just to show you how rich the detail can be, we have this image here, and here are the different categories in the image. So you have the different people that are segmented, but you also have their ties, or in this case, I guess it's bow ties, the baseball bat, the baseball that this person is holding. So some really, really rich information. And again, if you want to do some object detection in images, COCO is a really good place to get started. They also have a key point detection data set. So we have over 150,000 people and 1.7 million labeled key points. So again, like we saw with the stick figures, this is a really good data set if key point estimation is something that's interesting to you, because you can imagine that training a network that learns to recognize people requires a lot of training data. So now I want to give you some tips for collecting your own data set, or even labeling your own data set. Labeling data sets can be very, very prohibitively expensive. Usually it's human annotators that do it. So for example, in the context of ImageNet, they crowdsourced it using Amazon Mechanical Turk, where anyone could just sign up and get a few pennies every time they would classify an image. Now you can imagine that if you're doing that, you have to have all sorts of redundancies, because maybe two people disagree, so you have to have many evaluators evaluating the same images. So one thing I recommend is first start by looking for similar data sets to what the task you're trying to do. Perhaps there are lots and lots of data sets out there. I only mentioned a few that are used relatively often in literature, but there are many, many open source data sets. So first, look for similar data sets and understand the kind of labels you need and how you want to represent them. What's the task you're trying to do? Is it just classification? In that case, the label is relatively easy. It's just one label. If you're trying to do object detection, then all of a sudden you need to have bounding boxes. So how do you represent these bounding boxes. And again, I recommend you look at how other people have done that, and we're going to look at this later today as well. So another important point, labeling can be expensive and inaccurate. So if you don't have experts labeling your data, so if it's data sets that deal with pathologies, for example, I really don't recommend you go online and crowdsource that information. You might want some pathologists who are well trained to be able to identify structures. It could also be that these pathologists have to actually make measurements in a lab to get these results. So there are some ways that you can generate synthetic data. So for example, you can think of a simulator. If you're trying to build a self-driving car, you might want to build a virtual environment to simulate driving a car in which maybe your neural network can learn from that simulator. You can also use GANs to generate images. So we saw that GANs can generate some realistic looking images. So maybe you might want to train GANs to generate some more data. This can work well to test ideas, but it can also fail to generalize. So you can imagine that, say for example, you're learning based on a simulated environment. There can be some hints, if you will, in the simulator that the network might pick up that don't necessarily represent real life. So be careful when using synthetic data and have some means to validate that your synthetic data can actually translate well on a well-defined test set. Which leads to the next point. Be sure to have a robust and well-guarded test set. Don't use it too often. At some point, you as an architect for your deep learning networks will start to overfit on your test set. So just like the neural network can overfit on your training set, you can act as a sort of overfitter on your test set, because you will try things over and over and over and evaluate on your test set, even though we tell you not to do it. And then eventually, you'll pick the best architecture that worked best on your test set. So somehow you begin overfitting on your test set. So it's really important to safeguard your test set. And in fact, many competitions online will never release the test set. They will give you instructions as to how you can evaluate on their test set, and then you'll get maybe 2 or 3 evaluation submissions, and they'll take the best result based on those. And finally, always challenge the validity of your data. Make sure that it comes from a reliable source. Make sure that when you're feeding it to your neural network, it makes sense. You can do all sorts of transformations to your data. It can happen somewhere along the pipeline that your data doesn't either gets transformed in some way that doesn't make sense anymore. So try to visualize your data as much as you can throughout your pipeline. There's a really interesting story here that I recommend you go read. It's from one of the contributors to TensorFlow, and he kind of goes through the details of this horror story that happened where he worked on a model for years and perfected his model until he realized that, well, the problem was a bit more complicated than what I'm going to explain, but he says it's kind of similar to if you had the labels in your file name and you were reading the file name to build your classification algorithm. Right? And it sounds like a trivial error, but these can happen very easily. And if your network can cheat, it will figure out a way to cheat. So always question the validity of your data, and always make sure that you have some tests in place to be sure that your networks are working as you expect them to work.